Welcome back to the Machine Learning 101 course. Today we will go deeper into regression, more specifically linear regression. Quick recap of what we have learned so far. We discussed how machine learning differs from traditional programming. As in machine learning, we expect computers to learn without being explicitly programmed. We also got introduced to supervised learning, where the training data contains both input features and the labels to predict. Finally, we did a hands-on exercise to train a linear regression model. That helped us get a feel for the different stages in a machine learning model's lifecycle. We have already used the term linear regression multiple times. Let's learn what exactly it refers to now. Keep in mind that the formula f of x is equal to wx plus b is the same as the formula for a line y equals mx plus c.
Recall that a training set in supervised learning includes both the input features, such as the size of the house, and also the output targets, such as the price of the house. The output targets are the right answers that the model will learn from. To train the model, you feed the training set both the input features and the output targets to your learning algorithm. Then, your supervised learning algorithm will produce some function. We'll write this function as lowercase f, where f stands for function. Historically, this function used to be called a hypothesis, but I'm just going to call it a function f in this class. And the job of f is to take the new input x and output an estimate or prediction, which I'm going to call y hat. And it's written like the variable y with this little hat symbol on top. In machine learning, the convention is that y hat is the estimate or the prediction for y. The function f is called the model. X is called the input or the input feature, and the output of the model is the prediction y hat. The model's prediction is the estimated value of y. When the symbol is just the letter y, then that refers to the target, which is the actual true value in the training set. In contrast, y hat is an estimate. It may or may not be the actual true value. Well, if you're helping your client to sell the house, well, the true price of the house is unknown until they sell it. So your model f, given the size, outputs a price which is the estimated, that is the prediction of what the true price will be. Now, when we design a learning algorithm, a key question is, how are we going to represent the function f? Or in other words, what is the math formula we're going to use to compute f? For now, let's stick with f being a straight line. So your function can be written as f subscript w comma b of x equals, I'm going to use w times x plus b. I'll define w and b soon, but for now, just know that w and b are numbers, and the values chosen for w and b will determine the prediction y hat based on the input feature x. So this fwb of x means f is a function that takes x as input, and depending on the values of w and b, f will output some value of a prediction y hat. Let's plot the training set on the graph where the input feature x is on the horizontal axis and the output target y is on the vertical axis. Remember, the algorithm learns from this data and generates a best fit line, like maybe this one here. This straight line is the linear function fwb of x equals w times x plus b. Or more simply, we can drop w and b and just write f of x equals wx plus b. Here's what this function is doing. It's making predictions for the value of y using a straight line function of x. So you may ask, why are we choosing a linear function, where linear function is just a fancy term for a straight line, instead of some nonlinear function like a curve or a parabola? Well, sometimes you want to fit more complex nonlinear functions as well, like a curve like this. But since this linear function is relatively simple and easy to work with, let's use a line as a foundation that will eventually help you to get to more complex models that are nonlinear. This particular model, as a name, is called linear regression. More specifically, this is linear regression with one variable, where the phrase one variable means that there's a single input variable or feature x, namely the size of the house. Another name for a linear model with one input variable is univariate linear regression, where uni means one in Latin, and where variate means variable.
W and B are also called model parameters or weights. Given that x is an input variable, all we need to do is to learn a linear regression model to figure out what the value of w and b is. Not any value will work. We need to figure out these values such that we are able to make predictions with high accuracy. Sometimes machine learning might feel like magic, but in reality, it is mathematics. Earlier, we mentioned that we want to find model parameters such that it has a high accuracy. But how do we measure the quality of a linear regression model? The most commonly used metric is called root mean squared error.
A standard way to measure error is called RMS error. Let me show you how to calculate this. Let's suppose we use this data, which are these green points, to build a model. Let's say it's a linear model like this. We can assess the model at each real data point, for instance at this data point, and measure the difference between the y value of the data point and the model. And this difference is error. Now we've got an error at every single one of these data points. And what we do to measure root mean squared error is to take the error at each one of these points, square it, add them together, take the average, and take the square root of that. So that sounds kind of complicated, but here's what it looks like. Y test minus Y predict. So Y test are the actual values of the data. Y predict are what our model predicted. We take that difference at each point, that's this difference, square it, sum all those together, divide by the number of points, and take the square root. And that's our root mean squared error. And what this is an approximation of really is sort of the average error here. But we end up emphasizing larger errors a bit more.
This symbol represents summation. Here we are adding the square of all errors. And we square the errors because some errors can be negative. In the last week exercise, we calculated root mean square error twice. First for the training data, that tells how well the model performed on the data it was trained on. But our goal is to do well on unseen data. That's why a more reliable metric to measure model quality would be the root mean square error on test data, because test data was not part of model training. In our exercise, we predicted SAT score based on a single input feature, GPA. But for most real-world problems, single input feature is not enough to train a good quality model. Linear regression equation can be extended to include multiple input features. In the case of two input features, linear regression model represents a 3D hyperplane. For every input feature xi, there is a corresponding weight parameter wi that is learned as part of model training. And this is another way to write the same equation in a way that is more concise. From this scatter plot, it is clear to see that the correlation between GPA and SAT score is nonlinear. Hence, fitting a straight line is not going to help. Therefore, we're going to include some nonlinear features to improve the performance of the model. Another important topic is data reduction and cleansing. Remember, our ML model is only as good as the quality of the data it learns from. In our hands-on exercise, we worked on a very small and clean dataset, but that is uncommon in real-world data. Let's understand some of the common data reduction and cleansing steps involved in preparing data for machine learning.
One of the most crucial data preparation processes is data reduction and cleansing. Wait, what? Reduce data? Clean it? Shouldn't we collect all the data possible? Well, you do need to collect all possible data, but it doesn't mean that every piece of it carries value for your machine learning project. So you do the reduction to put only relevant data in your model. Picture this. You work for a hotel and want to build an ML model to forecast customer demand for twin and single rooms this year. You have a huge data set with different variables, like customer demographics and information on how many times each customer booked a particular hotel room last year. What you see here is just a tiny piece of a spreadsheet. In reality, there may be thousands of columns and rows. Let's imagine that the columns are dimensions on the 100-dimensional space with rows of data as points within that space. It will be difficult to do since we are used to 3 space dimensions, but each column is really a separate dimension here. And it's also a feature fed as input to a model. The thing is, When the number of dimensions is too big, and some of those aren't very useful, the performance of the machine learning algorithms can decrease. Logically, you need to reduce the number, right? That's what dimensionality reduction is about. For example, you can completely remove features that have zero or close to zero variance, like in the case of the country feature in our table. Since all customers come from the US, the presence of this feature won't make much impact on the prediction accuracy. There's also redundant data, like the year of birth feature, as it presents the same info as the age variable. Why use both if it's basically a duplicate? Another common pre-processing practice is sampling. Often you need to prototype solutions before actual production. If collected datasets are just too big, they can slow down the training process as they require larger computational and memory resources and take more time for algorithms to run on. With sampling, you single out just a subset of examples for training instead of using the whole dataset right away, speeding the exploration and prototyping of solutions. Sampling methods can also be applied to solve the imbalanced data issue involving datasets where the class representation is not equal. That's the problem Amazon had when building their tool. The training data was imbalanced with the prevailing part of resumes submitted by men, making female resumes a minority class. The model would have provided less biased results if it had been trained on a sampled training dataset with a more equal class distribution made prior. What about cleaning them? Datasets are often incomplete, containing empty cells, meaningless records, or question marks instead of necessary values. Not to mention that some data can be corrupted or just inaccurate. That needs to be fixed. It's better to feed a model with imputed data than leave blank spaces for it to speculate. As an example, you fill in missing values with selected constants or some predicted values based on other observations in the dataset. As far as corrupted or inaccurate data, you simply delete it from a set.
In the hands-on exercise, we will continue to work on the SAT prediction model. This time, we will introduce two new features, GPA squared and GPA cubed. The final performance of the model is shown in the graph, and it is much better than the model we trained last lesson. To try another problem and get some experience with data cleaning, look at the problem.md file in the repo. I have included a data cleaning notebook and my approach to the problem. In the next lesson, we will understand how linear regression model figures out the best parameters as part of model training. In addition, we will learn about the risks of underfitting and overfitting, along with tips on how to avoid this. Finally, we will learn about handling categorical values using a technique called one-hot encoding.